right, this is Monday afternoon, 2:08. Sorry we're late getting started. I ran over in my last class and had to do a couple things before I could come back and start this one. But I was waiting for somebody to show up too, and no one has. I'm in the class all by myself. It's supposed to be differential equations, Math 238. So I guess we'll just get going. Another thing I've been trying to do is warm up the room. The thermometer, the thermostat set for 68, but it feels a lot cooler than that, and it's warmer outside than it's inside, so I've opened the windows, and it's very slowly warming up. I've still got cold air blowing down on me, so I hope I can make it through the whole time. That was one thing I did during the break, is run down to my office, and I was real tempted to just move down there, but no one showed up in my Cal 3 class, so I wish I had been down there recording it because it's warmer there, but because someone may show up in this class, I decided to leave it up here. So anyway, let's pick up this couple of announcements. One is this coming Friday, well, my office hours this week, as far as I know, should be normal, okay? Monday, Wednesday, as soon as this class is over, 3:15 to 5:15. Tuesday and Thursday from 1:15 to 3:15. But Friday, there I have no office hours because the school is closed on Friday. Veterans Day this year is on a Saturday, that's November the 11th, and we have, and they're giving us Friday off rather than Monday. So Friday will be the day off. The campus will be closed, no classes will meet, no office hours on Friday. So if you have a Friday class, it will not meet this Friday. Check with your instructor first, make sure, but I'm pretty sure it won't. And there just are nothing going on then. So anyway, there's that. Number two, I just wanted to, this is just my little bag here, I wanted to encourage all of you. I think all three of you are greater than 18 years of age, or at least I think you are. And if I hope all three of you are eligible to vote. You may not be. One of you may be less than 18, or perhaps not a citizen. I don't know. But the others, if any of you are eligible to vote and are not registered, please register. There's a special election for the Senate seat coming up on December 12th. And sometime before the end of this month, you can still register and vote in that. I don't know the exact date, but it's toward the end of the month. So please register now, okay? Early educated. If you're not registered, please register. And if you are registered, please plan to vote, okay? This is a very important election, and it's crucial for you young people to get into the habit of voting. My wife did the numbers on it, and in the primaries for this Senate seat, the maximum percentage of votes gotten by any candidate was 8% of the eligible voters. That's not a democracy, okay? So few people came out to vote that 8% won in one of the primaries and fewer than that won in the other primary. It's just depressing, okay? There should have been something on the neighborhood of 50% of the voters voting in each primary. Of course, they're not all going to vote, but even if half of them voted, that would have been 25% in each or one of the primaries. Neither one of them had close to that. And please get out there and vote. Get into the habit of voting every time the polls are open. That's my little soapbox. I'll get off of it now, but really want you to vote. All right, now, where we left off last time was in Chapter 4, Higher Order Differential Equations, 4.1, Preliminary Theory of Linear Equations. This is one long section, okay? It's split into 4.1. There was a 4.1.1, then a 4.1.2, and we're wrapping up 4.1.2, and we'll hit a 4.1.3, okay? So let's continue in 4.1.2 on page 125, and this is, hey, there may be a student coming in. Yes, there is. Good to see you. Missed you in the Cal 3 class, but glad you're here for this one. All right, let me rearrange things now. Just finished making an announcement. Sorry if the room's so cold. I opened the windows to warm it up. But it's not all that warm outside either. But didn't it feel warmer out there than it is in here?
Yeah, it does, yeah.
Yeah, so, but the thing is, it's blowing cold air out, and I think it's just blowing cold air out of here out the window, you know, so, anyway, the two announcements I was going to make, I take it you probably don't have any classes here on Friday, do you?
No.
Okay. Friday is, the, I guess, official state holiday for Veterans Day. Veterans Day is actually on Saturday. So we do not have the school will not be open on Friday. Okay, so if you're going to come by for help or use the library or anything else, office hours, nobody will be here on Friday, except the police maybe, and they'll have it mostly locked up. Okay. You're at Tuscaloosa, right?
Yeah.
Do y'all have classes on Friday, or do you know? You don't? Okay.
So, I mean, like, I'm
You don't?
not there this semester. I'm actually down here working.
Oh, I see. Okay. Okay. All right. Well, then there are no classes here on Friday. This Friday. Okay. And the other thing I was harping on before you came in, since you may not go back and listen to it now, are you registered to vote?
Am I registered?
Yeah.
Oh, yeah.
All good. And you know about the election coming up in December?
I haven't been paying attention.
Well, you need to start paying attention, okay? Remember when Jeff Sessions became the Attorney General, he was a senator from Alabama, U.S. Senator, okay, one of the two, Richard Shelby and Jeff Sessions. When he became Attorney General, that left us without one of our senators. Well, that was early enough in his 6-year term that we should have had a special election, but the governor at the time decided to appoint his Attorney General, which was Luther Strange, to the Senate seat. It seemed to be, now no one's proven this, but everybody sort of got the idea, it was a quid pro quo, so he wouldn't pursue any of the charges that were being leveled against the governor. So he accepted the Senate seat, because that's what he really wanted, was the Senate seat. So Luther Strange became our senator by appointment, which was not the way it was supposed to be. Well, his assistant attorney general, who became attorney general, he proceeded with the investigation, and the governor resigned, okay, forced out. Well, the new governor came in, who was the lieutenant governor, and Kay Ivey, and she said, no, we were should have had an election for the Senate seat rather than an appointment. So we're going to have an election. So we had primaries back in September, I think it was, and then the Republicans had a runoff in their primary, and that was probably October, and now in December we vote for one of the two candidates, a Republican and a Democrat. And by the way, Luther Strange lost in the runoff with the Republicans. So he is our senator now, but he won't be after December 12th or sometime shortly thereafter. So anyway, this is for the Senate seat, the official election for the Senate seat. It's a special election, only one going. So a lot of people probably say, oh, I'm not going to go just to vote on one person. Go just to vote on one person. Please don't fail. Please do not fail to vote. No. Please vote. I'll put it that way. Please vote. Okay. All right. My wife did some calculations on it, and in the primaries, because this was sort of a special thing, the guy with the maximum number of votes in either primary had 8% of the electorate. 8%.
Really?
Yes, that few people voted in the primaries, and that's ridiculous. That's not a democracy. That means 8% of the people may have chosen who's going to be our next senator. That ain't right. So we need to get out there and vote. I'm not going to tell you who to vote for. I'm not going to tell you anything else, but vote. In this election, more than just about any other, your vote really, really may count. I think it's going to be pretty close, so please don't fail to vote. Please vote. Okay. Please. Okay. December 12th. That's real close to finals, but it's, yeah. Are you living at home now or wherever you're registered to vote?
Yeah.
Okay, you're not registered in Tuscaloosa. Are you? Yeah, okay, good.
Yeah, I'm close here at home.
Yeah,
Here,
okay, good. Be sure you do it. Okay. All right. We're, and this was the other thing I was saying before you came in, we're in Chapter 4, Section 4.1, which is Preliminary Theory, Linear Equations. And like I was saying before, this is one long section. 4.1 is broken into 4.1.1, which we finished, 4.1.2, which we're almost through, and then there'll be 4.1.3. Okay, well, we got a little ways to go there too. And let's see, yeah, finally that'll be it. So we're kind of in the middle of 4.1.2. So let's continue there. Last time we had just done Theorem 4.1.3, criteria for linearly independent solutions, and I think we had done all that. And we had talked about the definition. I can't remember. Were you here last Wednesday?
No.
Okay. So I don't know if you got to listen to it or not. But anyway, we introduced this thing called the Wronskian, which is a determinant. Okay. Have you done determinants before?
Probably have. Can't remember.
Yeah. Okay. Well, let's do this example and maybe it'll come back to you. Let me pick up where we were. I'm trying to recall. I'll back up a little bit. Here's a differential equation. Let me get my pen activated. Okay. X squared y double prime plus 7x y prime plus 13y is equal to 0. Okay? That's a differential equation. On the interval 0 to infinity. That's a pretty ugly infinity. Okay? That's for x's. Okay? Note that the coefficient functions, this is your a2 is x squared, your a1 is 7x, and your a0 is 13. Okay, those are your coefficient functions. Okay, they're all continuous functions, especially on that interval, but they're continuous everywhere. Okay, and the a2, a sub 2, x squared, is not equal to 0 anywhere on that domain, okay? And luckily, we excluded 0. So that's why we had to say from 0 to infinity. The functions were continuous everywhere, but you don't want this one being 0 anywhere in the interval. So that's why we excluded 0. We could have done negative infinity to 0 and excluded that way. Or we could have done 7 to 15. That would have been fine. You know, anything, we just could not include 0. Okay? So, they've met those criteria that they are continuous and on that interval, and A2 is not 0 on that interval. Okay. All right. So what is our Wronskian for this differential equation? Oh, I'm sorry. I started too far down. Needed to go back up. I was going to say, they haven't given us our solutions yet. There's a differential equation, and they say these functions, and by the way, y1 is equal to cosine 2 log x over x cubed and y2, didn't put my of x here, but it is, okay, is sine of 2 log x over x cubed. Okay. They said these two are solutions for that differential equation on that interval. Okay? Now, usually I like to stop and let's verify those. Okay? And we could, but that's going to get a little on the messy side. Okay? Let's just take the word for it this time that those two are solutions for it. Okay? Here's another reason we have to exclude 0, and this is why we can't include anything negative. The logs here. Logs are not defined for x equals 0 and not defined for anything negative. So this means we have to do something on that side of 0. You don't have to start at 0. You can start at 15. You go up to 145 or anything there. Just can't have 0 or any negative number within that because of this. Okay, there's 2 logs there. Nor could the 0 be because of there. Okay, because you could have a negative down here, but you can't have a negative here. So that's why that domain makes sense. Okay. The real part of me that wants to go on and do the derivatives. But it's just going to take the rest of the board and probably then some. Okay. But with those two being our solutions, okay, what the question is, are these linearly independent solutions? Okay? Now, I don't know about you. I can't look at those and say, oh, yeah, I can tell they're linearly independent. No, those are really weird-looking functions, okay? Yeah. So now I can't tell that. So here's what the Wronskian is. The Wronskian, and this is for these two functions, y1 and y2, is this. It's the determinant of they call it F1, but the same as y1. y1 and y2, that's the first line. y prime, y1 prime, and y2 prime. Sorry, I put the prime in the wrong place. Okay? That's all you need for this one. Okay? That determinant. Now, a determinant of 2 by 2 is very easy to do. Okay? It's just, well, I'll show you in a minute. But here, we're going to have to do the first derivative of each of those. So now I really wish I had done them. We don't need to do the second for a Wronskian, but we could have done it to check. So let's first do, y1 prime. What is it? Okay. All right. Let's do it. Let's rewrite these. Okay. Let's write this as. Okay. I'm going to erase some of the stuff above it because we've already talked about this, and so we don't need this. I just need more room. Okay. I'm going to rewrite that just because I like to do it this way. Do you like the quotient rule or do you like the product rule better? I do too. So let's write it this way. Cosine of 2 log x times x to the minus 3. You okay with that? All right, and then do this one too. In fact, I'm going to write the x to the minus 3 first. X to the minus 3 times the sine of 2 log x. That way it's not confusing. So let me put this x to the minus 3 in front. Okay? Now we can do a product rule on it. Okay? So y1 prime is going to be, and which do you want to do first? You want to do first times derivative of the second, or second times derivative of the second. So the first here is x to the minus 3. What's the derivative of a cosine? Negative sine of 2 ln x times wait, no, you got a chain rule thing to do.
Oh, yeah, chain rule, I'm sorry. That's not, that's the third time. That would be
Derivative of the inside,
divided by 8.
2 over x. Okay, that's it. Plus, that's just the first times derivative of the second. Now it's the second times derivative of the first. What's the derivative of the first? Okay, so that's not going to be a plus, it's going to be a minus. Okay. 3 times x to the negative 4 times the cosine of 2 log x. Okay. Now, I want to point something out to you. This is 1 over x cubed, and this is another x down there. So this is over x to the 4th. That's over x to the 4th. So I don't know if it's helpful to write it that way or not, but I'm going to. Okay. This will be, I'm going to pull the minus on the outside. And it'll be sine of 2 log x, 2 times sine of 2 log x, minus, pulling the minus on the outside, so that's going to be 3 cosine of 2 log x, okay, over x to the 4th. Is that all right? Huh?
Yeah.
Okay. Because I pulled the minus out front, and this will give us a 2. I'm sorry, this 2 times the sine of 2 log x over x to the 4th, and pulling the minus out here, plus 3 times cosine of 2 log x, and both of those are over x to the 4th. X to 3 and x there, and x to the 4th there. Okay. So that's your first derivative of your y1. Okay. Somewhere I've got to find room to write the other, okay? I'll write it over here, so I'm going to need this room later. y2 prime, I think we can pretty much, we've already written it up here, and what would be its y2 prime? Okay, but you want to do the first x to minus 3 times cosine of
2
right times 2 over x. Okay, very similar to what we had before, but with a plus sign here, not a minus. This will have a minus sign, and it'll be x to the minus 3, the first time derivative of this. No, I'm sorry. Derivative of the first times the second. Okay. And what's the derivative of the first?
Derivative of the first is negative 3x raised to negative 1.
All right, times the sine of that thing, 2 log x. Okay. And that's, okay. And we can also rewrite this as 2 cosine 2 log x minus 3 sine of 2 log x. Sorry about this. Oops. Yeah. all of that over x to the fourth. Because this had, again, this had a 1 over x cubed and 1 over x, that gives you 1 over x to the fourth, 2 times cosine minus 3 times sine over that. So they're very similar. This one, both of them are negative. That one's the first is positive, second is negative. But anyway, now we can write a Wronskian. Where we'll write it, I'm not sure, but less, you know, we're not going to use that differential equation any. It just told you these were the solutions for that differential equation. So I'm going to go up here and just erase the differential equation. Sorry, but if I need it, I'll copy it down again. But this is just not enough room on this little screen. If you had been here for the last class, it got so frustrating. I was trying to write on here. Well, I've already erased more than I meant to. Okay, let me put some of that back. Okay. So I'm going to do the Wronskian up here. Now, I don't know if you remember how to do a determinant. You said probably not. Okay, how do you determine the determinant of a 2 by 2 is you this product minus that product.
Yeah, the cross product?
It's like a cross product, only it's a minus, not equal. It's this product minus that product.
Okay.
Okay. So your y1 is here, just this thing, that thing, okay, and your y2 prime is that. So we're multiplying this times that. Okay? Now, so this will be your y1 is x to the minus 3 cosine of 2 log x times, okay, the y2 prime, which is 2 cosine of 2 log x minus 3 sine of 2 log x over x to the fourth. Okay? Minus, okay, the y2, which is that one, times y1 prime, which is this one. Okay? And this is all negative, that one's positive, so that minus is going to actually become a plus. Okay? And what you have here is x to the minus 3 sine of 2 log x times this one down here, and I already took care of the signs here, and this will be a 2 sine of 2 log x plus 3 cosine of 2 log x, all divided by x to the fourth. Okay. I know that's messy, sorry. Okay. Now the question is this Wronskian zero? If it is, these two are not linearly independent functions. If it's not zero, then they are. Okay? So let's see what we've got here. Here we have a 1 over x cubed cosine 2 log x, and here we will have a 1 over x fourth. So we got something over x to the 7th. Okay? And here we have a 2 cosine squared 2 log x minus 3 sine 2 log x. And down here we have, again, your denominators are the same, x to the 7th. And here you have a 2 sine squared 2 log x, okay, plus 3 cosine 2 log x. Well, think about here, cosine squared 2 log x plus sine squared 2 log x. They both got a 2 in front of them. So that becomes just 2, right? Because cosine squared plus sine squared is 1. Okay? But then you have a minus 3 sine of this and a plus 3 cosine of this. Oh, by the way, multiplied by these two. And it's just not any way that's going to be a 0 ever. I mean, so that is not 0. And that's all we had to show, that it's not 0. The value of it really doesn't matter too much. It's just that it's not equal to 0. Okay?
That they're independent?
What's that?
So what does that mean? What is not equal to 0? That means that
The Wronski. This thing, this product minus that product cannot equal 0. All the terms that were canceled out, well, let's be a little more careful about it. Okay? Here we had, remember, 2 cosine squared 2 log x minus 3 sine 2 log x cosine 2 log x. And down here we had a 2 sine squared 2 log x, and 2 cosine squared plus 2 sine squared give us 2. 2 times 1 is 2. So that's 2. And here we have plus 3 sine 2 log x cosine 2 log x. Well, up here we had a minus 3 sine 2 log x cosine 2 log x. So those do add to 0, right? Minus 3 sine 2 log x plus times cosine 2 log x plus 3 sine 2 log x times cosine 2 log x. Those do add to 0, but this adds to 2. Okay. So your determinant is 2. Well, it's 2 over x to the 4. No, x to the 7. No, yeah, x to the 7. 2 over x to the 7. That's, and if I already erased our range there, but anywhere that x is, that's not equal to 0. Of course, x can't be 0. Okay? So, the Wronskian and we did it for all values, but what they said here, rather than expanding this unwieldy determinant, why didn't I read this before? We choose x equal 1 in the interval 0 to infinity, and find if we put a 1 in there, well, I didn't want to do that, okay, x equal 1, what's the log of 1? 0, okay? So this would be 0, 2 times 0 is 0, and this would be cosine of 0 is 1 over 1, okay? This one would have been 0, right? Yeah. Log of 1 would be 0, sine of 0 is 0. So you'd have had a 1 and 0 here, and down here, let's get this form, that's our simplest form. When x is 1, log is 0, so this one would be 0, so this would be a 3 over 1, so that one would be a 3, and this one would have been a, this would be when x is 0, log is 1, so this would have been 1, and that would be, that would have just been 2. I can remember we had the 2 there. Yeah.
that's what I was looking at.
Yeah, this would have been a 2. So we would have had a 1, 0, 3, 2. That would have been our Wronskian. 1, 0, 3, 2. What's that determinant? 2 minus 0.
Yeah.
So that would be 2. It's not 0. It's not 0. Well, what I just showed is 2 everywhere. Okay? Because the first one would have been a 2, and the second, no, I'm sorry, that's not quite right. It would have been it would have been 2 over x4. X7 everywhere. And so you choose x equal 1, x equal any number you want to. It's not going to be 0. They just chose it for 1. Now, how they could get away with that? The fact that the Wronskian is not 0 is sufficient to conclude y1 of x and y2 of x are linearly independent on 0 to infinity. Okay? They just chose it for one value of x, but they're saying it would work, and it would have. The way we did it, it showed it would. Okay? Now, with that done, let's hit the wrong key. All right, erase all this link and go to a system of n linearly independent solutions of a homogeneous linear nth order differential equation is given a special name, and here's what it is. Any set, okay, y1, y2, y3, that's a 3, dot, 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 up to and including y sub n, right? Yeah. Okay. Of n linearly independent solutions of the homogeneous differential equations nth order differential equation, DE, and that was back several pages back. This is equation number 6. On some interval I, okay, is said to be a fundamental set of solutions. Okay, on that interval. Okay. Now, what we're saying then, I'll back up. We have a homogeneous nth order differential equation on I. Now remember, this section is only dealing with, this section is only dealing with linear equations. Okay? So we have a homogeneous nth order linear differential equation on I. Okay? Now remember what that means. It means your coefficients can have any kind of x's in them, they just can't have any y's. Okay? And that is times the nth derivative, some other coefficient, depending on x alone, but no y's, times the n minus first derivative plus some other coefficient that could have any x's in it, just can't have any y's. Okay? And all the way down until you get to some coefficient of x times y prime times some coefficient of x times y. Okay? Now this coefficient of x again can't have any y's in it. Okay, so that y is only first term. And these other derivatives don't have any y's in the coefficients, and they don't have any other derivatives in the coefficients. Just x, the nth derivative, the n minus first derivative, the n minus second derivative, down to the second derivative, the first derivative, the zeroth derivative, which is the function itself, is equal to 0. That's what makes it homogeneous. Okay? Okay. So, we have the nth order homogeneous equation. That means there will be n solutions. If you have a set of n solutions that are linearly independent of each other, that all solve that equation. You can't have more than n. They won't be linearly independent, guaranteed. But if you can find n that are linearly independent, that's what is said to be a fundamental set of solutions. There's only one of those? No, you could have the set made up any way you want to, but we're going to talk about later, they're going to span the same set, the same space there. We're not there yet. Okay, so that's what we're talking about. Okay, a basic question of whether a fundamental set of solutions exists for a linear equation is answered in the next theorem. I think I'll write this down. Theorem 4.1.4. There exists a fundamental set, okay, of solutions. That's LNS, I can't write very well. For the homogeneous linear nth order differential equation. For the homogeneous linear nth order differential equation on interval I. Okay. There exists a fundamental set of solutions for, in other words, if you have a homogeneous linear nth order differential equation on some interval I, you can find some fundamental set of solutions. There will be n of those solutions, and they'll all be linearly independent of each other. You can find a set of n solutions that aren't, that's not a fundamental set. But if you find any fundamental set that they are linearly independent, there's n of them, that's your fundamental set for that equation, a set. Okay. Now, analogous to any vector in 3 dimension can be expressed as a linear combination of your I, j, and k unit vectors. Same thing here. Any solution to a linear homogeneous nth order differential equation can be set as a linear combination of those of that fundamental set. Okay, y1 through yn. In other words, they're the basic building blocks, and you can get your general solutions from any of those. So here comes another theorem. I love these theorems, don't you? Okay. Don't have room to write it on that slide, so let's go to a new one. And this is it. Okay. Let y1, y2, y3, ... up to yn be a fundamental set of solutions okay, of the homogeneous linear nth order differential equation on some interval I. Seems like there should be a shorthand for that. I've written that so many times now. That's going to be the case. Okay, that's a fundamental set. This means, if that's true, the general solution okay, of that equation on that interval is this. Y is equal to C1, Y1 of x plus C2 y, get carried away, okay, cy2 of x plus C3 y3 of x plus dot 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 plus C sub n y sub n of x, okay, where the CIs from I equal 1, 2, 3, dot, 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 up to n are arbitrary constants. Okay. Now, what does that mean? If you have this fundamental set of solutions that are linearly independent of each other, you have n of them for this homogeneous nth-order linear differential equation. That's the most you can have in that fundamental set on that interval. Then the general solution, you can write y, and you take any c's that you want to put down there. Those will be, if that's the solution, that's the solution, that's the solution. All those are solutions you can multiply by any constant, any one of them, but any constant you want to, add them together, those will be a solution to. Okay? That's what we mean by the general solution. Every solution out there can be written in that way. Okay. Those are constants now, not constants of any variable, just constants. Okay. So that states that if y of x is a solution, okay, of all that stuff that we said, on some interval, then the constants, C1, C2, all the way up to Cn, can be found so that that is a linear combination of those, that fundamental set. Okay? It says we'll prove that for the case n equal 2. I don't know if you want me to go through the proof. It turns out being, it almost feels like it's circular, but it does show it basically beyond the shadow of a doubt because of the good old Wronskian, okay? The Wronskian, because they're linear and independent, can't be zero, and yet everything pans out so they are not. Let's move on to example 7 and actually do that one. Rather, whoops, hit the wrong key again. Yuck. My boy, in the last class, I tried to get a bigger, because, I mean, that's the screen you see here. That's not the size of this screen. That's a little box within my screen. And I'm having to write everything in that little box, so that's why it looked like I'm writing big there, but I'm writing as small as I can get away with here and be readable to me and not having things jammed together. And I tried to, this is called the presenter mode or something like that, which is a real pain in the neck. So my other computer, I could leave the presenter mode alone and just write on the whole screen. And I did that for a certain way, and then it wouldn't let me erase. It wouldn't let me do anything. It got hung up, so I had to go back to presenter mode. I thought I had tried it before, but this computer is different from mine, and I don't know how, but it will not let me do that. So, or I don't have enough sense to know how to make it not so. So here's example 7. Here's a y1 is going to be e to the 3x. Okay? Here's a y2, that's going to be e to the minus 3x. Okay? they're both solutions, it says, of the homogeneous linear equation y double prime minus 9y is equal to 0. Okay? Now, and that's on the interval everywhere. Minus infinity to infinity. So it doesn't matter what x you choose. There's no holes, there's no gaps, no breaks. It's continuous everywhere. Now this one's pretty easy to check, I think. Okay, what's the first derivative of this? Y1 prime.
E to the 3x.
Times 3.
Yeah, that's it.
Okay. And what's the second derivative?
9 to the
9 e to the 3x. Okay. First derivative is here.
negative 3 e to the negative 3x.
And what's the second derivative?
Positive 9 e to the negative 3x.
Okay. So if you were so this one, okay, let's do that. So it's 9 e to the 3x minus 9 times e to the 3x. That's going to be 0. And this was 9 times e to the minus 3x minus 9 times e to the minus 3x. That's going to be 0. So yeah, both of these are solutions on that. Okay? Now, what's the first thing it asks us to do? It says they're both solutions on the interval. By inspection, the solutions are linearly independent on the axis. Okay, why do they say it that way? Anywhere on the thing. Now, how do we tell they're linearly independent? You do the Wronskian, which is e to the 3x, 3e to the 3x, right? That's what you said first derivative was, right?
Yeah.
Okay. And e to the minus 3x minus 3e to the minus 3x, right? Okay, let's take the determinant there. This will be minus 3e, minus 3, right? Because e to the 3x times e to the minus 3x is 1, right? Okay. And then minus 3 is equal to minus 6. And that's not equal to 0. So, yeah, pretty obvious those are linearly independent. Okay? Now, yeah, they just did the same thing we did. Okay? Did I write it wrong? Oh, I did write it wrong. And it really doesn't matter. The Wronskian was F1, F2.
So you're saying like on the top row?
Yeah.
You're saying it would be F1 and F2?
Yeah.
Well, Y1, Y2?
Yeah, Y1, Y2. And then the second row is the derivatives. So this would be what? Okay. This would be 3, and that's your minus 3. Okay. This is a minus, yeah. And that's a plus. Okay. Now you do your Wronskian, or your determinant. That would be minus 3 minus 3. Same thing. If you exchange those are called transposers of each other. I transposed the matrix, and the determinants are the same. I shouldn't have transposed it. Yeah, it didn't matter. Okay.
So does it matter what order you put them in when you're using the
yeah, if you write the functions on the top row and the derivatives on the next row, or if you write the function its derivative and the second function its derivative, those are transposed of each other. It doesn't matter.
Okay.
But you're supposed to write it function,
Yeah,
first derivative, first derivative.
Okay.
I just did it wrongly. Okay. So these are linearly independent. They're both solutions. We verified that. They're linearly independent. So we conclude the general solution is y is equal to NEC1 e to the 3x plus NEC2 e to the minus 3x. There's your general solution for that equation. That's the only solution you get. I mean, there's infinite number of them depending on what C's you choose. 1 and 0, 0, 1. Certainly 0, 0 would work, but that's not very interesting. Minus pi thirds for the first C and square root of 2 for the next C. I mean, any C's you can put there, that's everything of that form is going to be a solution. Okay. So there's infinite number of them. Okay. That's a general solution on that interval. Okay. Let's go to example 8. Here's a function. Oh, I love this one. Y is equal to 4 times the hyperbolic sine of 3x minus 5 times e to the minus 3x. Okay. Now, did you, in your cal sequence, do hyperbolic functions?
That sounds very familiar.
You did? Okay. All right. I usually don't because they can be written as exponential functions. I thought, why come up with another name when you can write them as exponential? But we'll do it. Okay?
Come up with the sign of H.
What's that?
Never mind, you can see it.
Yeah, it has really nothing to do with sines at all. It's called hyperbolic sines. The reason because the derivative functions and things like this are similar but not quite the same as the trig functions.
Yeah.
They have nothing to do with angles or trigs. They all have to do with exponential functions. And it just happens to be, they call them hyperbolic trig functions, though they have nothing to do with trig functions. To me, I don't care for them. And except for things like this, I never use them. You know,
Yeah.
I'm not saying no major. What's your major, by the way?
Civil and architectural.
Say again?
Civil and architectural engineering.
Engineering, okay. Maybe somewhere you'll use a hyperbolic sine or cosine. I doubt it.
I haven't.
Yeah, I don't think you will, you know. But mathematicians love them because it's another function you have to fiddle around with. Okay. Now, that function, they say, is a solution to the differential equation in example 7. Wow. Okay. So they say that is and this is exactly what I was saying, okay, is a solution of that differential equation as well. They say verify it. Well, to verify it, you have to do y prime. Now, do you happen to know what the derivative of hyperbolic sine is?
I had it on the phone with you, but
Okay. If you go to your, do you have a book? Your book bag's behind you.
oh, okay, I like that.
Yeah.
I was like, man, I know I came in here with it.
Okay, front and side cover. Very first thing you get to. See functions, review of differentiation, the number 21. You see it? No, yeah, on this
Oh,
side.
this side. Okay. Yeah.
This hyperbolic cosine. Right?
Yeah.
So its derivative would be hyperbolic cosine, COSH of 3x times 3, so you would have to multiply the 4 times 3, and that would make it 12. Right? Okay. Minus, now this part's a lot easier. Actually, it becomes a plus, doesn't it? 15 e to the minus 3x. Right? Okay, let's do y double prime. That would be, I'll tell you, 12 times 3 is going to be 36. And the derivative of hyperbolic cosine, if you'll go down to the number 22, is hyperbolic sine. So that's SINH. You see, there's a difference. Derivative of sine is cosine, but derivative of cosine is minus sine. Well, derivative of hyperbolic cosine is sine, hyperbolic sine. So it just enough, it's so similar, but just enough difference to just get you in the problem. Okay, 3x, and this will be minus 45 e to the minus 3x. Agreed? Okay. Now, does that satisfy the differential equation we had before? And that differential equation was y double prime minus 9y equals 0. Well, let's see if it does. Y double prime here is 36 hyperbolic sine 3x minus 45 e to the minus 3x. That's your y double prime. Minus 9 times 4 hyperbolic sine of 3x minus 5 times e to the minus 3x. Is that equal to 0? It claims it is. Is it? Well, 4 times 9 is minus 36. Those will wipe out. And 9 times 5, minus 9 times minus 5 is plus 45. That's minus, yeah, it will be. So that is. So therefore, can you say that this solution is a linear combination of your other two? They don't look anything close to being the same. Well, I don't know if the tables are in this book or not. These are Laplace transforms. Okay. I'll have to tell you what is a hyperbolic sine. And this is of 3x. Is equal to, let me just leave it as u, hyperbolic sine of u. Right. Yeah. Okay. Is e to the u minus e to the minus u over 2. That's what a hyperbolic sine is. Has nothing to do with the trig function at all. Okay? So therefore, a hyperbolic sine of 3x, which is what we're dealing with here, would be e to the 3x minus e to the minus 3x over 2. Right? Yeah. Okay. So then let's write down this. That would be y is equal to 4 times e to the 3x minus e to the minus 3x over 2, right? Minus 5e to the minus 3x, right? Instead of the hyperbolic sine of 3x, I've written in that, this thing right here, right? Well, here the 2 will go into 4 twice. So this is 2 times e to the 3x minus 2e to the minus 3x minus 5e to the minus 3x. And guess what we got? This is 2e to the 3x minus 7e to the minus 3x. That's the solution. Of course it is. Because this is some C1 times the first one, we have already erased it, plus some C2 times the same. So yeah, this is a linear combination of those because that's what hyperbolic sine is. It's a linear combination of e to the u to e to the minus u. So no big surprise. So why have a hyperbolic sine when you could have just written this as e to the minus e to the plus? I see no purpose in it. There must be, or else they wouldn't have them. But okay. They did it really bizarrely, but they did it. Okay. So y is equal to 2e to the 3x minus 7e to the minus 3x. Yeah. All right, do we have time to do example 9? Let's try it. I don't know if we do or not, but let's try. The functions y1 is equal to e to the x, y2 is equal to e to the 2x, y3 is equal to e to the 3x, satisfy the third order equation y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. Okay? We ain't going to have time to do this, but let's at least get it started. Okay? Start with this one. Y triple prime here would be
e to the x.
yeah, e to the x. Because first derivative would be e to the x, second derivative would be e to the x, third derivative would be e to the x. First derivative of that would be
2e to the
x, second derivative would be 4e to the x, third derivative would be 8e to the x. Okay, this one would be first y is that, y prime would be 3 to the x, y double prime would be
9e,
and y triple prime would be
18e.
27.
Huh?
27.
Oh, yeah, 3, 9, yeah.
All right, let's see if each of those work. For e to the x, that would be e to the x minus 6, e to the x, that would be minus 5 e to the x plus 11 e to the x, that would be plus 6 minus 6. Yeah, that one works. How about this one? Remember, that would be 8 e to the 2x minus 6 times 4 would be 24. So 8 minus 24 would be minus 18. No, it's minus 16.
Yes.
Minus 16 e to the 2x, and this would be plus 22. So that would be plus 6 minus 6 is 0. All right? So let's do the 3x. That would be 27 e to the 3x minus 6 times minus 54. And that would be plus 20, minus 27, right? Plus 27 minus 54.
Yeah.
Okay, minus 27 e to the 3x, and then minus 33, no, plus 33, and that was minus 20, so that's plus 6 minus 6 equals 0. Yes, all three of those are solutions for that. Okay? They satisfy the third. Okay. Now, all we have to do is do the Wronskian for that. Okay? E to the x, e to the 2x, e to the 3x. E to the x, 2e to the 2x, 3e to the 3x. And e to the x, 4e to the 2x, and 9e to the 3x. That's our Wronskian, right? The functions, the first derivatives, and their second derivatives. Okay? When you take the determinant of it, now I don't know, have you hit this before? To do a 3 by 3, now this is the only one that works on this, but it will, okay? You can do this, write down the first two columns, e to the x, e to the x, e to the x. Second column, e to the 2x, 2e to the 2x, and 3 and 4, e to the 2x, okay? Now what you do here is go down your diagonals, okay? And that would be 2 times 9 is 18, e to the, you add these together, 6x, right? Okay, go down this diagonal, okay, plus, and that would be 3 e to the 6x, right? Go down the third diagonal, okay? And that would be plus 4 e to the 6x. Minus, now this time you go up the diagonal, so that's why the minus sign is there. And that would be 2 e to the 6x. Go up this diagonal, and that would be minus 12 e to the 6x. I left off my x here, didn't I? And then go up this one, and that would be minus 9 e to the 6x. Okay, add those together. This is 21, and 4 is 25 e to the 6x, and this is minus 21 and 2 is 23 e to the 6x, and that's not equal to 0. Okay, so the Wronskian is 2 e to the 6x, and that's not equal to 0. Okay, so therefore those are solutions. That's a fundamental set. So you can say your general solution is y is equal to c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. Okay? Any linear combination of that, that's your general solution. All right, sorry, we ran over. Whoa, we ran over 5 minutes. No extra charge. Okay. All right, it'll be covered in your tuition. All right, let's end this. Oh, homework exercises. Okay. I've already given you some of these. Any of the odds, either 1 or 3 or both. Either 5 or 7 or both. Do number 9 and do number 11. Do number 13. That's all in 4.1.1. 4.1.2, any of the odds 15 to 21, and any of the odds 23 to 29. All right, and then we'll pick up next time with non-homogeneous equations, which you'll find pretty straightforward after this one.